All right, everybody, so we're going to get started. So today's topic, we're going to be talking about neural networks. And this has been a topic that we've been leading up to throughout the semester, doing kind of more basic algorithms like linear models, logistic models, and stuff like that. And this is one of the cooler and more complex algorithms that we're going to go through today. And it is a little complicated, so again, at any point, if you're confused, just let us know and we will answer your questions.
So to start, we're going to phrase the problem that we're going to use to explain how neural nets work. So we're going to try and take an image of a handwritten digit, and we're going to try and teach a computer how to figure out what number that is. So in this case, you can see a handwritten 3 that's not perfect, it's got weird edges, and we want to figure out how to tell a computer that this should be a 3. And to start, we can think about how would your brain do this. If you think about it, you can take any 3 and you can break it apart into multiple different components. You can take a piece at the top, this curve right here, and this circle at the bottom, and these 3 components together represent a 3. And your brain can discern between different types of shapes, even if they're imperfect, to find what the actual output is.
All right, so now let's talk about the data we're going to actually be dealing with. So the data we're dealing with is a Mnist Data Set. That's the name of the data set. And the input images are going to look exactly like this. They're going to be 28 by 28 pixels. All right, and there's going to be 10 different classes. So the 10 different classes represent 10 different possible numbers that you could get, because we're trying to classify handwritten digits, so the possible numbers can range from 0 to 9. And this is what the data set looks like. It has about 70,000 images. So once we kind of input all these images into what we're going to be talking about, it's going to have a really good idea of how to classify what each image looks like. And so it's really important to know that within these image pixels, the pixel range goes from 0 to 1. So a black pixel would have a value of 0.0, and a white pixel would have a value of 1.0. And in between represents a gray scale. So that's really important in understanding what the inputs are going to look like, because our model is going to take this image as an input.
And neural networks are the particular type of algorithm we're going to talk about to solve this problem.
All right, so let's talk about how an algorithm might attack this problem. So it starts by taking this image, and like a computer can't look at this image. It has no way of seeing what the image looks like. It has to split this image up into individual pixel values. So again, the image is 28 by 28 pixels, which means within the image, 28 times 28, there are 784 pixel inputs. All right, and this is just a numerical visualization of what the image actually looks like. We're taking the image and all of its pixel values and just crunching it in a one-dimensional vector of all of the pixel values. And then what our neural network does, in short, is it processes this image of a 3 into what Addy called subcomponents, which are just tinier chunks of the handwritten 3, and it's looking at these subcomponents and it's trying to combine them in all different types of variations. So maybe these two together, and shuffling these subcomponents around until it finds something that it recognizes. And once it does find something that it recognizes,
it represents that as it puts that out as its output. So for our particular neural net, we're going to have an output which is just 10 different numbers. And associated with each one of those numbers, so 0 through 9, which are different classes, there's going to be a number between 0 and 1. That can be thought of as a percentage probability that this image has that digit in it. So for example, if you look here with a 3, the 3 output will have the highest percentage probability because it realizes that's a 3. Whereas any other digit will have a lower percentage probability. And all of these predictions will add up to 1 because that's the whole percentage probability.
So the output is really just a list of values, each value corresponding to a different class, 0 through 9. And supposedly, if our model works, the class that is inputted will have the highest value, or the maximum value. All right, so now let's talk a little bit more about what a neural network looks like. So we can split it up into 3 different parts: an input layer, a processing layer, and an output layer. as we said previously, the input layer takes these pixel values as input. And then the processing layer splits up the input into subcomponents. And this is like maybe how a neural network would work. It doesn't necessarily have to work this way, but this is one way of a neural net attacking this problem. Splitting it up into subcomponents, combining the subcomponents, and then seeing if those combination of subcomponents relate to something that it's seen before. And if it does relate to something it's seen before, it will say, hey, this kind of looks like a 3. Let me output the maximum probability for the third class. Well, because it's 0 indexed, it would be 0, 1, 2, 3. And this node would have the highest value. And you're seeing all of these circular kind of nodes here. Those are called neurons. And they're basically just containers for values. So in the input layer, the values in the neurons are going to be pixel values. And those are, there are some computational calculations happening in the processing layers to output whether the computer is looking at something that looks like a 3 or a 4 or a 5. So all you basically need to know is you have some pixel inputs and there's some kind of calculations going on here that determines what this image actually is.
Now to understand what's actually going on inside a neural net, because there's a lot of different things, we're going to isolate just one neuron. So in this case, we can have one neuron in our first processing layer and all of our input neurons. And what we see here is that the input neurons all together produce an output in this neuron, and what that means is whether or not it thinks that a particular shape or a particular edge exists in that network, in that image. And so that's the purpose of each neuron, is it solves one particular problem, so it could be looking for one particular edge or one particular shape.
So now, how does this happen in the network? So let's say that we're focusing on this bottom loop. So in a 3, this bottom loop is characteristic in almost any 3 you write. So if we're specifically looking for this bottom loop, certain part of the images, certain parts will be more important than others. Because if we're looking for a loop that exists at the bottom, the pixels in the bottom half of the image, or the bottom third of the image, are way more important than the pixels above that bottom loop, because we're specifically looking for this subcomponent. So that means that certain neurons, certain pixel inputs, will be more important than other pixel inputs, because the more important pixel inputs correspond to the bottom third of the image. Maybe, for example, we were looking for the middle of the 3, where the first loop and the second loop connect. Then the middle third of the image would be most important, and so the most important pixels would correspond to the middle of the image. So it's really important to understand that some pixels will be prioritized when you're looking for certain things. And that prioritization is stored as a weight. And a weight just says how important is this input value to what we're trying to do. So how important is an input corresponding to what we're looking for. And then another example would be looking at, I don't know, the top part of the 3. So the top kind of straight line of the 3, and the most important pixels there would be the top part of the image. So it's just really important fundamentally to understand this idea, because certain pixels will have different importances, and those importances are represented in weights. Weights are just values. They're values that denote how important a pixel input is. And so you can kind of think of weights as knobs and dials, a way to adjust the network's prioritization of different pixel inputs. And this is generalized over a bunch of different inputs. So now it's important to talk about, there's more to neural networks than what we just talked about. We only talked about the input, right? We only talked about what happens when a neural networks get pixel inputs, what happens in the hidden layer. But the neural network actually has to learn what weights to assign to different nodes to make the model really, really fine-tuned, really accurate. And so that learning process is a little out of the scope of what we're talking about today. But if you'd like to learn a little bit more about that, there's a YouTube channel on there's a YouTube channel on machine learning. It's called 3 Blue 1 Brown, and there's a specific video, 2 videos, back propagation and back propagation with calculus, that explains how neural networks learn. But basically, boiled down, a neural network will output a prediction, and based on how lousy that prediction is, it will readjust its weights to make that prediction closer to what it should be. So at this point, we gave you a bunch of information. So does anyone have any questions regarding like the way neural networks work, the input structure, anything about that? Okay, so if you guys have no questions, we can move on to the interactive walkthrough section. So just to review what we're going to be doing, we're going to have a neural network that looks sort of like this. It's going to have 784 inputs. It's going to have 2 layers of processing where it identifies what the actual handwritten digit looks like, and then it's going to have an output layer that says, what is the image I'm looking at? What is it actually, what is the class that it fits into? And that's going to be outputted in this kind of list type of format with probabilities. All right. So now we can go here. Let's make sure this is being shared. Okay, great. So for everyone here and online, make sure to go to Google Collab. You can just write Google Collab in Google, and that will direct you to an online IDE that we'll be using in today's walkthrough. So anyone who's having trouble getting to Google Collab, all you have to do is literally just type Google Collab in Google, and then you can just press the first link, sign into your Google account, and then just create a new notebook. And that's how it will show up, just like this. Is anyone having trouble getting into Google Collab? Okay. So we're going to split up this interactive walkthrough into a few sections. So we're going to have a section that focuses on importing the data set, visualizing the data set, cleaning it up, creating our neural network, and then actually seeing if our neural network works. So let's start with the part where we actually import the data set. So I'm assuming everyone's in Google Colab. So let's start. Is everyone good? Good? All right, great. So we're going to import a few modules, but we're going to go one module at a time. So we need to import our data set. So if you do from keras.datasets, import Mnist, that is the data set we're going to be working with today. If you run that and that fails to run, then you need to pip install keras. So if anyone has any trouble getting this to work, you just have to pip install keras and it should work after that. But there are a lot of libraries pre-installed into this, so I don't think you should have any errors with this. So go ahead and import that library in, and now we're going to be importing our data. So one thing that's really important, neural networks accept data in the form that we spoke about before, 784 pixel inputs, but we have to split up our data into training data and testing data. That's super important because we want to allocate a lot of our data for the model to understand the structure of the data, what it looks like, how to classify certain images, and then we want to allocate a little bit of the data to see whether our model actually works. So that's called training data, where the model learns, and testing data, where the model tests its knowledge. So the way to import training and testing data is like this. You have some arbitrary variable names, xtrain, ytrain. You can name these whatever you want, but it's important that they're characteristic of testing and training data. Xtest and ytest. And you need to assign these two sets of values to mnist.load_data. All right. If you run this, it basically downloads the data from TensorFlow API into your notebook so you can manipulate it. So yeah.
So what is the data set we're training?
So the data set we're using is the Mnist Data Set.
So Mnist is a standardized open source data set, and it's pretty common to be used for teaching. And also there's a new one called Mnist Fashion, but it's very similar to this one.
Yeah, it's the handwritten data set that we covered before. It's the same thing. Yeah.
We have a question back there?
I'd say emphasis on separating training versus testing is because we don't want the network to memorize, which it can do with large
Absolutely.
Absolutely, yes.
Yeah, there is a lot of issues in the field, like with certain neural networks actually memorizing the structure of data. So that's why test train split is really important.
Yeah, and usually it's randomized which samples it picks. And also actually with Mnist, that's a big problem because there's some tricks you can use to memorize the structure of the Mnist data set where you can pretty much figure out what digit it is based on like 3 pixels.
Yeah, and then that also, mini batching comes in with that, but that's a little bit more complex.
Yeah, it's more
so now we want to look at what the structure of our data set actually looks like. So like the dimensions of our inputs and our outputs. All right, so first let's print the number of training images. And the way we do this is concatenating this string with the shape of our X-train data, specifically the first index. All right, so we have 60,000 training images. Just training, we're gonna have 10,000 testing images. So the way you visualize that, you can just do the same thing, but with X-test. So testing images, and then just X-test.shape. And you'll see that we have 60,000 training images and 10,000 testing images. Now, what are the dimensions of our inputs? Remember that our input is an image, so the dimension of our inputs is going to be 28 by 28. All right? So now that we know the dimensions of our inputs, how many training and testing images we have, let's try to output what a handwritten digit might look like in our Python environment. All right, so a lot of times with data visualization, you're going to be using a library called Matplotlib. So you can import matplotlib.pyplot as PLT. And then the way you just display an image is you do plt.imshow. And then you can pick, a random sample in your data set. So we'll just pick the first sample in our data set. All right, so that's what the handwritten digit looks like. Now notice it's actually not the same as the type of digits we saw in the presentation. Adi, do you want to explain why?
So part of it is that we're doing with a different class. Also for visualization purposes, it's actually making it colored. In order to increase the performance of our model, we want to get rid of that. You don't actually need the colors. You can do grayscale. That's what we're going to do with our model. And so just for visualization purposes and for high contrast, they make it colored.
Right. So we visualized a 5, and you can actually go through the data set and identify like objects of certain classes, so like digits of certain classes, because this data set is completely labeled. So remember we had that X train, X test, Y train, Y test. Y basically means the label of the image. So those two correspond. So X will be the image and Y will be, is it a 3, is it a 4, is it a 5? Right, so let's say we wanted to display all the images that were 3s, for example. So the way you would do this is you would create a for loop. And then in the for loop, you go through Y train and you say if an index of Y train is equal to 3, then show the image. And because X train and Y train are corresponding, you're able to do this really easily.
And basically what we're getting out of this is that we're trying to find any images of class 3, so we're printing all of the handwritten digits which are of the class 3 in our training data set.
And this line of code is really important, plot.show. That is super useful because if you don't write plot.show, then it's just going to rewrite the image over the first image, so you're only going to get one output. So really important, plot.show, so you get multiple outputs. So if you run this, you're getting a bunch of different images of different variations of 3s. So you can see that the 3s don't all look the same. The thickness is different, the position within the frame is different, the orientation, the rotation. So a model is not looking at the same image of a 3 over and over and over again. It's looking at different images of a 3. And so it kind of has to do what we talked about. It has to kind of look at the features of the 3 and make a generalization of what it's looking at. All right, any questions on that? So yeah, you can do this with any class. So if you wanted to change that to 7, for example, you could go up here and if ytrain I equals 7 and do the same. And you would get outputs of a bunch of different 7s. All right. This is just a way to show you how to access individual images within your data and also how to access entries in your data that fit a certain class. All right. So what Adi talked about, what we can do is we can normalize our data. And the way we normalize our data is dividing the pixel values by 255. Because colored pixel values go between 0 and 255. So the way you normalize images is just do xtrain equals xtrain divided by 255.
And for this particular data set, it's 255 because the range is between 0 and 255. But for any general data set, you just want to divide it by the possible range of values. So it could be like some other constant, or you just find the maximum value and then divide by that. That way you get everything between 0 and 1, which fits into our neural net.
All right. So now that we've normalized our data, it's time to build the neural network. So the model you're going to need to, or the library you're going to need to use is TensorFlow. So import TensorFlow as TF. This, if you're dealing with machine learning in any way, TensorFlow is probably going to be one of the most important libraries to understand how to use, and it's probably one of the more frequently used libraries. So really, TensorFlow is a great tool, and it's really very well used in the field. All right. So now let's build our neural net. Adi, why don't you explain what I'm doing as I'm writing the code?
Okay, perfect. All right, so the first thing we're going to do is we're just going to say neural net equals tf.keros.sequential. All this is telling us, all this is telling Keros actually is that we're using a sequential neural net. So it goes from one layer to the next to the next.
That's just basically chronological. And now we're adding layers to our neural net, right?
So this first one that we're going to have is our input layer. So as we mentioned, our images are 28 by 28. And so you'll see in a minute that Nolan's going to write input shape equals 28. That's 28 comma 28. That's just going to tell it that we're expecting a 28 by 28 input.
And so what flatten does is 28 by 28. It's going to give you a two-dimensional array. Flatten, what it does is it just flattens that two-dimensional array into a one-dimensional array that the neural net can accept. Because again, it can accept a two-dimensional array of 28 by 28, but it can accept a one-dimensional array of 784 elements. So that's what the flatten layer is doing. And now we're actually going to get into the neural network layers, the stuff that's actually going to do the work to classify what we're looking at.
Okay, so the next layers that we're going to add are what are called hidden layers. We call them processing layers. They're just different names for the same thing. The first layer is going to have 16 nodes, and this is going to be seen when Noam writes 16. And the second layer will also have 16 nodes. Now, we picked this because we thought it would work well with finding different shapes. But in actuality, you have to play around with this particular setup for and see which one works best. There's not really a formula for that. You just have to do trial and error until you find an architecture that works. As well, you can see it's saying layers.dense. All that means is that every neuron is connected to every neuron in the previous layer.
So remember, in our presentation, we had these neural networks, right? And you can see that every node is connected to every node in the next layer and every node in the previous layer. So this is a fully connected network. That means every node is playing some role in what's happening in the next layer. All right, so that's what a dense layer means. What does activation mean? So activation functions allow us to get our values between 0 and 1. And we're going to use a different activation function for the last layer. But you can think of an activation function as limiting the possible range of values we have for our output so that our output is actually something that makes mathematical sense. I also encourage you guys to do more research past this because this is a very elementary introduction to neural networks with not too much math. So if you're really into math, definitely check out 3 Blue 1 Brown's videos. All right, so now we have the final layer. So we have this input layer that we talked about, the 2 processing layers that theoretically might identify subcomponents, and then we have our final layer.
So this we call our output layer. This actually tells us what class the neural net thinks the image falls into. So it's going to have 10 different neurons. This is because there's 10 different classes. And this is also going to be a dense layer, so it's fully connected to the previous layer. And you'll see that there's an activation equals softmax. We need to use this because of some properties of our previous activation functions. We're not going to go into that right now because that's outside the scope of this lecture. But definitely look into the way activation functions work, and you'll pretty quickly figure out what these are.
So we took the model, the neural network that we talked about previously, with 784 inputs. We have 2 processing layers, each with 16 nodes. As Adi said, this architecture isn't something that's ubiquitous for this problem. A lot of people specialize in understanding what architectures are best for each problem. You can play with the amount of nodes in your dense layer after we're done with the lecture and see that that drastically affects the accuracy. You can also play with different activation functions. So architecture is not something that's concrete. You can play around with it, and a lot of times people will iterate through different values of nodes and see what outputs the best accuracy. But because the training time for these algorithms are relatively high, we don't have too much time to do that in the time provided. So we built our model. Now let's get a summary of what our model actually looks like. All right. So as we said, we have our input layer, 784 inputs, and then our 2 processing layers and our outputs. So you might be asking, what are these numbers? What are these parameters? So parameters correspond to weights. Trainable weights, basically numbers that define how important each pixel input is. All right? And so you see this value, total trainable parameters. That means the total amount of weights that can be adjusted to make the output as accurate as possible. All right? So this just allows you to look basically what your model looks like. And a lot of times when people make really complex neural networks, they'll use this .summary method just to see what it looks like, see the input and output shapes and the number of trainable parameters they have in their model, which gives you a basic idea of how long it will take to train the neural network. All right, so now we have our architecture. Now we want to train the network. This is the fun part where you get output. What's going on?
So for the output shapes, when it's like 9,74 or 9,16, what does that actually mean?
So output shape is just how many nodes you have.
Oh, okay.
Yeah. So 784 nodes in the first layer, 16 nodes in the next layer, 16 nodes in the next layer, 10 nodes in the final layer. Yeah. Any other questions? Did I answer your question?
Yeah.
Okay, cool. All right, so now let's actually train the model. Training the model means the model is going to start with a random amount of weights. So it's going to randomize these 13,002 weights, and it's going to continuously adjust those weights over time to reach a model that is super fine-tuned to dealing with this problem. So this is how we do it. Neural net dot compile, and then we need to use some optimizer, and this is just how we're optimizing the weights in our model. Again, if you want to do a little bit more research into what optimizers do, go for that. Optimizers just allow you to adjust your model's accuracy really like a lot quicker than just doing it the vanilla gradient descent way. So we're going to choose our optimizer as Atom. Our loss function, or our error function, is going to be categorical cross entropy. And I'll explain this in a moment. So a loss function defines basically the error of your model. So there are many ways to define the error of your model. You can take the predicted output and subtract it from the actual output and square it, and do that, and take the sum of that over your entire training set. But when you have more than 2 possible outputs, when you have 10 possible outputs, you need to use an error function that can calculate error for more than 2 outputs. So this loss function, categorical cross entropy, allows you to calculate error for more than 2 outputs, and it does it really well. It uses a method called one-hot encoding. And so I can explain one-hot encoding really quick because I think it might be of interest to you guys. So let's pivot the screen to the whiteboard. Let me know if you guys can see the whiteboard. So what we said was there are different ways of calculating error of a model, right? One way is mean squared error, which just it's equal to the difference of your actual and predicted values squared. And then this is over the entire sum of your size of your model. Like the size of the training set. The problem with this is that this doesn't account for more than a binary output. It's not really good for outputs that are more than binary. So categorical cross entropy allows you to encode your outputs instead of 0 and 1, which is binary, to look like something like this. Since we have 10 possible outputs, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you can encode your outputs instead of this. If we were trying to represent a 3, you would put a 1 here and a 0 in every other position. This basic orientation of representing classes allows you to use this loss function, which is a lot more effective for multi-class problems. Whereas this doesn't really know how to deal with multi-class problems as well. And you'll see that if we replace the loss function with mean squared error, the production and the accuracy of the model will be terrible. So that's really categorical cross entropy, quickly explained. And again, feel free to do more research into that. And if you have more questions after the lecture, feel free. All right. So for our model to actually use categorical cross entropy, we need to adjust the y train and y test variables. So the way we do this is y train equals tf.keras.util.to categorical. And this is going to transform our y train and testing data into something that categorical cross entropy can accept. Y train, and then the number of classes is equal to 10. all right, because there are 10 possible outputs. So this is transforming our Y our Y training data and our Y testing data, which is like the output, the real output, into something that categorical cross entropy can deal with. And then the same goes for Y test. It's important to note, do not run these two lines of code more than once, because you'll get an error. It will screw up your error because it's adding another dimension to Y train and Y test. And if you run it more than once, it's going to add another dimension, another dimension, another dimension, and the neural network can't work with higher dimensionalities than 2 for training data in this case. So we've compiled the model, we've adjusted training and testing, Y training and Y testing data to fit our loss function, and now what we're going to do is we're going to create a variable called model history, and this model history variable will essentially tell us the accuracy values and error values over time of our neural network. And the way we do this is we're fitting the model to some data. Go for it. Fitting the model to some data. We're splitting the data, as we said, into 80% training, 20% testing. So we'll say validation split equals 0.2. And then, Adi, would you like to explain batch size?
Sure, yeah. So batch size tells you how many images at once you want to run through with training, and then you'll find the error relative to what it should be at each iteration. You'll average the amount for that batch, and then you'll change the values all at once. So instead of every single image saying, oh, I've changed this way, changed that way, you can average out how much of an error it's making over a larger number of images. And so that way it's not too sensitive to training images.
Absolutely. All right. Does anyone have any questions about the code we've written so far? I just want to make sure that no one's getting lost.
Can I actually pull us a little back? The person in chat wasn't able to see the whiteboard, and I sent them an image. Can we just go over a little bit about the category cross entropy on the whiteboard really quick?
Yeah, so should I tilt the camera? Or?
They have the image itself.
So basically what we were saying was that usually neural networks that are facing regression problems, which are like line of best fit problems, they might use an error that looks like this. But because we're facing a problem that has more than 2 classes, it's multi-class, it has 10 different possible outputs, you need to encode the data to look like the output data to look like something like this, and then use a different loss function that's specifically trained for multi-class problems. Since this is not trained for multi-class problems and it's really for binary regression problems, it's going to be really hard for you to get an accurate output for this. So really the main idea is that this is not useful for multi-class, but this categorical cross-entropy is really fine-tuned for multi-class problems. We just have to adjust our data a little bit to fit this loss function.
Thank you.
All right. Now, here comes the fun part. We've initialized everything. Now we're going to train our model. So if we run this node, oops. I think I spelled something wrong. Oh, it's utils. Here we go. There we go. All right. Now if we run this node, so we're going to get an output that looks like this. And what's going on here is that the model is actually training. So loss is another way of saying error. So you'll see that the error is decreasing over time. And you can also display accuracy. I'll show you guys how to do that in just a moment. But this is what the training process looks like. So if you're training neural networks with TensorFlow, this is what training looks like. Epochs is the amount of iterations you're training the model for. Does anyone have any trouble getting this to work? Okay. So if you wanted to display the accuracy of the model, which is like pretty important, what you would do is add an argument here called metrics, and then set that equal to accuracy. What's important is If you run this again, you're going to get an error guaranteed. I'll run it again and I'll show you guys that there will be an error with dimensionality. See, there's an error here. 32, 10, 10, and 32, 10 are incompatible dimensions because you're adding another, you're doing two categorical again. So for this to work, what you have to do is go to runtime and then run all. So you're rerunning everything, and this should take maybe 20 seconds to get to where we are, and then you'll be able to see the training process included with accuracy to kind of understand what the accuracy of your model is. So if you're having any errors with dimensions, let us know. We'll help you debug your code. All right, so now we have accuracy right here. What is accuracy? What is val accuracy? Accuracy is training accuracy, and val accuracy is testing accuracy. Okay? If anyone doesn't understand the distinction between training and validation, we can make that distinction for you again. So as the model is training, its validation accuracy reaches 95.1% about. Now, this is really good accuracy for Mnist, but if you are eager to make the accuracy 97, 98%, you could go back up here and adjust the architecture to make it fit the problem a little bit better, and you would have to play with different nodes, as Adi said previously, maybe play with activation functions, and get to a point where the accuracy is 98%. But for the purposes of this lecture, we're just going to focus on how to get the model to a pretty high accuracy rate. So now you have this neural network that works. Let's say you were trying to present your results, and you wanted to graph accuracy and loss over time. So the way you can do this is you can create plots with Matplotlib. Very simple. So just do plot.plot, and then model history, remember, is what we assigned neuralnet.fit. If you do model history.history, and then just index with whatever you want to look at, accuracy, and do plot.show, you'll be able to get a plot of the accuracy of the model, which looks like this. But this is a boring graph and it doesn't tell us too much about what's going on. Let's label it and add some relevance to it. Let's add some labels to the X and Y and a title. So the way you add a title to a graph in Matplotlib is you do plot.title, and you'll do a, we'll say val accuracy and training accuracy. So we want to plot both validation accuracy and training accuracy. And the way we do this is we just add another plot.plot statement with the same model history statement, but instead of regular accuracy, we can change that to validation accuracy. So just val accuracy. And then you're going to get a graph that looks a little bit better. And if you want to label the X and Y labels, super simple. This is why Python is one of the most popular languages for machine learning, because everything's quick and simple. You can just write plot.xLabel and then whatever you want. So in this case, the X is the amount of epochs or iterations. And then for the Y label, it's the accuracy. All right, and then it's important to note that the orange line is testing accuracy, and the blue line is training accuracy. Why is there this little discrepancy? When the model sees so much more data, it's probably going to get really accurate really fast. But when the model is testing on new data, it's never seen this data before, so maybe the accuracy will be a little bit lower. That's one hypothesis why the accuracy for the testing is a little bit lower. And then if you wanted to do the same thing with loss, you can just repeat this process. So you can just copy this entire code. Oops. You can just copy this entire code and replace accuracy with loss. And loss, again, is just a representation of error. All right, val loss. And training loss. And you'll see that the same phenomena exists in loss that the loss for training will be a little bit lower than the loss for testing, theoretically. Yeah. The loss for training will be a little bit lower than the loss for testing. Just because testing data is totally new in the model, it's never seen it before. Now, we've done a lot so far. We've plotted accuracy, loss, but what if you were actually asked to use this model in real life? Like someone gave you an image of a 3, and you were asked to actually like output a prediction. So that's the last thing we're gonna do today. I'll show you guys how to take the model that you built and apply it to data that's randomized, all right? So remember that the shape of our data is 28 by 28 when we first get the image, right? So let's create a variable called input, where we're grabbing a random sample from our testing data, all right? We'll call the random sample random int. And so we just need to randomize some value from 0 to 10,000 because we have 10,000 testing images. All right, so we can define random int equal to rand dot rand int. We'll say 1 to 10,000. And then all you have to do is import random as rand. And now we have our random integer, and we can even print that out if we wanted to. So we have some random integer, and that's defined as 7,776. All right, now let's see what that testing data, what that actual image looks like. All right. So what does the test data actually look like? So it looks like this. It's this image of an 8. Okay? We want to feed this into our neural net and see if it can actually classify this as an 8. No pre-processing has been done to this specific image, which means we're testing a colored image on a model that's trained on a black and white images. And you'll see that even when the image is colored, it will still be able to identify this as an 8. So now what we have to do is we need to create some output prediction and set that equal to our neural net, which is just the name of our model, dot predict. It's that easy. And saying for every class, what is the certainty that 3 is that class? So you see that for the numbers that are 0, 1, 2, 4, 5, 6, 7, the numbers are very low. They're raised to the 10 to the negative 4, 5, 6, 7, 8. But for 3, it's 9.991 times 10 to the negative 1. And the way to find the max, the indice with the maximum value, you can use NumPy. So if you import NumPy as NP, then you can do np.argmax and then your output prediction. And then if you do this, you'll get that the maximum, the indice with the maximum argument is 3. And there you go. You've been able to, you can now deploy your model on new data and output a prediction with about 95.1% accuracy. So first of all, thank you guys all for attending. Thank you for the patience. And for most of you who've been here, like the semester, thank you for supporting the club. This is going to be our last meeting. I really appreciate all the support I've gotten for you. And that's it. Do you have anything else to say?
Not much, other than you can play around with this more if you feel like it. You can mess around with the architecture, and you should be able to get up to 99.5% accuracy. So if anyone likes a challenge, go for it.
Yep. Thank you, guys. Appreciate it.